talk about note set 2 a little bit. We talk about binary. And I think to start, what I'm going to say is that if I wanted to compare languages, maybe I'll say that hello in English is the same thing as hola in Spanish. They are equivalent, just different representations. If I say goodbye in English, I cannot spell. If I say goodbye in English, that would be adios in Spanish. They are equivalent. When it comes to base 10 and base 2 numbers, we are going to represent something in base 10 in a different way, but they are essentially identical. But depending on the person that you're talking to, they understand it in a different way. So for example, maybe you are better at English, you understand this. Maybe, somebody from Spain understands that. Same exact word, but depending on who you are interacting with, they would interpret it differently. They wouldn't see it in the way that you want them to. Because if I say a sentence in English to somebody that doesn't speak English, it'll make no sense to them. But if I say it to them in Spanish, okay, now it makes sense. Similar thing, if I give you a number in base 10 and a number in base 2, this is for people. This is for they represent the same thing, but if I tell a computer, hey, 27, that's a number I care about, it will not necessarily know what that means. It has to translate it into something that it can understand. Similarly, if we were given a number in binary that a computer perfectly understands, do we understand it? Not necessarily. We have to convert it back to something that we're more familiar with. So even though we are representing a number in 2 different ways, they are equivalent, just like goodbye and adios are equivalent. Now let's talk about, let's break down this process again. Let's say I look at a number like 1,200, and I'll do 35. And this is base 10. We said in class that this is the same as 1 times, this is in the 1,000 spot, 10 cubed plus 2 times 10 squared plus 3 times 10 to the 1 plus 5 times 10 to the 0. If I want to make a table, I say, let's say I have 1,000 here, 100, and 1. Below would be, how many groups I have. So in this case, I have 1 group of 1,000, 2 groups of 100, 3 groups of 10, and 5 groups of 1. If you want to think about it like that. We can do something kind of similar in binary. Let's say I do 1, 1, 0, 1 in base 2. And we'll try to visualize it a little bit differently. I'm just going to start at 2 to the 0 and count up like that. And you know what? I'll actually write it out in full. 2 cubed, this is 8. 2 squared is 4. 2 to the 1 is 2. So instead of it being groups of 1, 10, 100, 1,000, it's groups of 1, 2, 4, and 8, and 16, and so on. So in this case, what we're asking is, do we have a group of that? Well, based on this number, I do have a group of 8. I have a group of 10 cubed. I have a group of 2 squared. I have of 2 cubed, sorry. I have a group of 2 squared. Do I have a group of 2 to the 1? Nope. And do I have a group of 2 to the 0? According to my binary number, I do. They do. So what we'll do is literally add these numbers up, the ones that we have a group of. And this is the number 13 in base 10. Again, I'm writing an equal sign here because they are equivalent. Just the receiving end of the conversation interprets them differently. If I'm a person and I say to you, hey, I have 13 pens in my cup holder, that makes sense. But if I say to you, I have 1101 pens in my cup holder, it doesn't make any sense to you. But if I tell it to a computer, it would make sense to the computer. Again, it's like the comparison between English and Spanish. It's a little bit different. Let's do another example. And actually, to come back to this is 1 times 2 cubed plus 1 times 2 squared plus 0 times 2 to the 1 plus 1 times 2 to the 0. Now I want to compare the binary stuff again. So I'm worried that this might make things more confusing, but I think it'll help. Let's say I have this number in base 10. This is 1,111. And I want to compare that to the same number in base 2. This means that we have one group of 1,000, one group of 100, one group of 10, and one group of 1. And that is, 1,000 plus 100 plus 10 plus 1. That is our 111 number in base 10. Doing this operation to a base 10 number is kind of useless because it just gives us the same number back. But if I do this in base 2, what this is saying is I have one group of 8, I have one group of 4, one group of 2, and I have one group of 1. You can see that the exponents here, match. The thing that changes is the number that's in the base. If I'm in base 10, those are 10s. If I'm in base 2, they're 2s. So this is going to be 8 plus 4 plus 2 plus 1. It's 12 plus 2 is 14 plus 1 is 15. So even though they look the same, because they are in different bases, they're completely different numbers. If there's a word in English that is written the same in Spanish, but they mean different things, that's a comparable example. I can't think of a word like that off the top of my head. A lot of times if they look the same, they probably mean the same thing. But when it comes to binary and base 10, you have to remember that we are expressing things in a different way. These numbers here are not related at all. There's no relationship to them in binary and base 10. I just did this as an example to show the math. We see 1 times 10 cubed versus 1 times 2 cubed. We end up with very different numbers. Let's do another example. Let's say I give you 1001.101. And maybe we can make a table. So I'll say that we have, this is our 2 to the 0, right? 1, 2, 3. So this is our 0 exponent. This is our 1 exponent. This is our 2 exponent. This is our 3 exponent. This is our -1, -2, -3. And again, this is base 2. So if we were to write this out, it'd be 1 times 2 cubed plus 0 times 2 squared plus 0 times 2 to the first plus 1 times 2 to the 1. That's this part, the whole number part that I just did. Plus 1 times, sorry. That should be 1 times 2 to the 0. Plus 1 times 2 to the -1 plus 0 times 2 to the -2 plus 1 times 2 to the -3. We do this out, that first term is 8 plus 0 plus 0 plus 1 plus 1/2 plus 0 plus 1. Why am I being terrible. Sorry, guys. It's a long day. Plus 1/8. So our whole number part will be 9 plus 1/2, which is 0.5, plus 1/8, which is 0.125. This is 9.625. It's 10. So again, English, Spanish, they're equivalent, but written out in different ways. So that's how we go from base 10, or sorry, from base 2 to base 10. The other way is a little bit more complicated. Those are our algorithms. So there's two algorithms. Let's say it takes some number like 17.35. Will that work? Yeah, I think it'll work eventually. Let's see. So this, and again, this is base 10. This is our whole number. This is our fraction. So we have two algorithms to use, one for the whole number, one for the fraction. Let's do the whole number first. So for the whole number, we have our value, our quotient, our remainder. Our initial value is 17. This algorithm says to divide it by 2 and look to see how many perfect groups of 2 we can make without going over. Well, the nearest even number is 16. That'll be a quotient of 8 with a remainder of 1. Just to write this out, this is 8 times 2 plus 1. This is our perfect group of 2. We have 8 of them, and this is our remainder to get to the 17. Remainder has to be 1 or 0. If our remainder is 2, well, it's just an additional group of 2. I would have 9 groups of 2, and that my remainder would end up being 0. So if our quotient is 8, that becomes our new value. Divided by 2, we have 4 perfect groups. Our remainder is 0. 4 divided by 2 is 2. Remainder is 0. 2 divided by 2 is 1. Remainder is 0. 1 divided by 2 is 0. Remainder 1. So if I were to write 1, 0, 0, 0, 1 in base 2, that is equal to 17. That's the whole number. We can prove this, right? Because this is an exponent of 0. 1, 2, 3, 4. This says that we have one group of 2 to the 4th plus one group of 2 to the 0. Well, that's 16 plus 1 is 17. We can check our work. Okay. Now the fractional part, the algorithm is a little bit different. And we had 0.35, right? We have our value, the product, and I like to write the word left. To remind me, I want the number to the left of the decimal. So with 0.35 and multiply that by 2, that's 0.7. What number is to the left of the decimal? 0. Use that same number for the decimal part of that number. Do it again. That's 1.4. To the left is a 1. I'm going to write the decimal part of this. The decimal part of this is this. That is what I just wrote here. Multiplied by 2 again, we get 0.8. 0. 0.8 times 2 is 6. It's a 1. We'll write the number without the front, without the 1. It's 1.2. That would end up being a 1. 0.2 would be 0.4. It's 0. 0.4, I did choose a crappy number because it's going to end up looping. 0. And then we're repeating at this point. And just to remember, we're going to go downwards here. We're going to go upwards here. It just happened to, this was by accident, it happened to be a palindrome, 1, 0, 0, 1, 0, 0, 0, 1. versus 1, 0, 0, 0, 1 end up being the same. That's not always the case. You always read from the bottom up. For the product, though, you'll read from the top down. So this is approximately, because we're cutting off some digits, 0.0101100, and then it would repeat base 2. So the 17, 10001, and then the 0.35 was the thing we just had. Let's come back to that and look. 01011. 01011. And you can add a few zeros, it doesn't matter. So 17.35 will just be the sum of those. 10001.0101100. We can double check it. So I'm going to stop sharing. How do I stop sharing? I stop sharing over here. And I'm going to share my screen here now. Share this screen. Let's do binary to decimal converter. And let's go ahead and enter in our number, which was in decimal. I'm going to convert that to binary. 17.35, if we convert that. 10001, that was our 17. 01011000, and then it looks like we repeat 1100, 1100, 1100, etc. And that's just because we cannot finish, what we started, because of the fact that this was a bad number choice. They just kind of chose that arbitrarily. So the moral of the story is that if you have a base 10 number, we need to understand that if we were to input that into a computer, it may or may not be accurate depending on how many ones and zeros our computer can hold. And that's like the example we saw a little bit in class today, where we did the square root of 3, where at some point we run out, or because the square root of 3 is irrational, we keep doing the algorithm, we'll just end up having additional ones and zeros, that at some point we'll just have to stop because we've run out of memory. We've run out in our computer the ability to store more information. So because of that, we end up with some sort of truncation error between our expression and our exact value. So note that our computers and calculators aren't perfect because they do not evaluate things to the exact true value if we do not have sufficient memory. And that's the purpose of why we're going over binary now. We'll talk more about this in class next time. Okay, I hope this was helpful. Please come to my office if you have questions. We could try to talk about it, and I'll try to think about different ways to explain it if there's confusion. Okay, thanks.